Hey, I bet you my car can go faster than your car.
What? No way. I feel like just because this one's heavier, it'll be pulled stronger by gravity.
Yeah, but mine's lighter, so it will be able to go a lot quicker.
Let's make a bet.
Okay, sounds good. I bet you mine can go quicker.
Let's figure it out.
How about we start with a ramp?
Let's do it.
So here's the ramp we're going to use. I started by taking a regular piece of paper and folding it into 45 degrees, and then again in half into 22.5 degrees. And that is pretty much perfectly the angle of our ramp.
Now, we use a slippery surface on purpose because we're going to assume it's frictionless. Alright, so we're going to get the masses out of the way, and I think this one's going to go ahead because it's heavier. So this one is 54.2 grams, and the lighter one is only 15.4 grams. Now that we're done the test runs, we're going to figure out some calculations.
So we're going to start with the free body diagram. So we started by drawing our incline that the car was running down. We drew the car by this brick right here, and then what we did was we drew the forces acting upon the car. So the first force here is the normal force, which acts perpendicular to the resting surface of the car. Our second force is gravity, which acts directly downward on the car. We also have our incline angle, theta, which in our case we knew was 22.5 degrees. Now, in this case, it's actually easier to choose our coordinate system as a tilted that's the same direction as the incline of the angle. And that way, we can calculate our vectors and our vector components easier. So, let's calculate some of these components. So our first step is we want to sum up all the forces in the x direction. Now, from our question, the x direction is the downward force that's perpendicular to the ramp. So this is just mg, which is our force of gravity, multiplied by our angle, or the sine of our angle theta. And that is because if we look on this line right here, and we draw our right angle triangle, this is actually the opposite side with respect to angle theta. So that's why we use the sine. Now, the sum of the forces in the y direction are just zero, because our car doesn't move in the y direction. It stays flat on the ramp and moves down. So because of the way we've chosen our coordinate system, we can say that the sum of the forces in the y direction are zero. Our next step is we can sum up the forces, so that our F net is just our mg sine of theta plus our zero. And we know from Newton's second law that force is mass times acceleration. So what we do is we plug our force in, and we plug our mass and acceleration in. Notice we drop the vectors because these are the summed components. Now, as you see, the masses cancel, and we're just left with acceleration is g sine theta.
Alright, so our last step is to calculate the final speed. And as we saw, the masses cancel here, so it won't even matter what the masses of the cars. They're going to have the same final velocity. So we're using kinematics fifth equation. We can see that final velocity squared minus the initial velocity squared is going to give us acceleration and position. So the initial velocity, as we saw, was zero because there was no initial force exerted on the two cars as they were about to go from a stop position. The acceleration is just going to be g sine theta, and the delta x will be 0.28 meters as we measured with the ruler. That means the final velocity is going to be the square root of 2g sine theta delta x, and 9.8 meters per second being our acceleration, and the 22.5 degrees as we calculated before being our angle, and the 0.28 meters. So if we plug that all in, we get 1.449 meters per second. I don't get it. I really thought this would have the advantage because it's so heavy. Just you would think that.
I know. I really thought that this one would go a lot quicker than that one because it was so much lighter. Neither of us won.
All right. Well, we
We figured out the speed at least.